Okay, so good evening everyone. So I'm Aniket Mukherjee from I'm doing my PhD. People are still joining, so maybe it's better. Should I wait for 2 minutes or like? Okay, I'll start. So my name is Aniket Mukherjee. So you can call me Aniket. No need to call sir and all. So I'm doing my PhD in ISC, DSC department, and so this is the week one for your. People are joining. So, what I'll do is okay. So what I'll do is I'll recap multi-arm bandits, that the part that sir has introduced, and I'll do the ungraded assignment solutions for this week, because sir has not still yet totally gone into algorithm analysis and different types of algorithms used for RL stuff and all. So we don't have yet. There's nothing to code up anything. So coding, we have small coding sessions. We would like to do some small coding sessions also. So we'll do that as the course progresses. But for the first part of the course, I want to keep it like really. Today I will keep it short and I'll just do a recap of what sir has stated. And I think I've seen one doubt in the forum. One guy has asked regarding pack complexity, so that I'll get to. And yeah, let me just do a short recap of multi-arm bandits. So essentially what the problem is that so multi-arm bandits, you have n sorry, you have n arms or actions, so which you can pull at each and every time instant t. Once you pull an arm at each time instant t, you get a reward RT. So what you want to essentially do is you want to maximize the reward that you get, expected reward that you get asymptotically. So that is what you want to do. So all the rewards that these each and every n arms gives is multiple people are joining. I'm really sorry because I'm getting the request from multiple people now, so it's ringing in my ear. So maybe it's better if I wait for some time. Right?
Hi Aniket, are you the TA?
Yeah, I'm one of the TA. You'll have two TAs for like
Perfect.
we will be taking the live sessions. Just yeah, we will be taking the live sessions for the RL course. So I'm one of the
Got
TA.
it.
You'll also have
Thank
and
you.
the yeah the okay. So it's just that still people are joining. So I don't want to start and again like pause myself to admit them into the Google Meet. So that I'm just taking some time so that I'll start at 6. See, so people are still joining still now, and I'm getting the request for them to join. So I'm waiting for most of them to just join. So yes, okay, so maybe I'll start. So since many of them have joined, I think after I've given my introduction, so I'll just start my introduction once again. So I'm Aniket Mukherjee. You can call me Aniket. So I'm doing my PhD in IIC DSC. So I'll be one of your TAs for this course. We have two TAs, me and another guy member. He will be also giving live sessions for me. And yeah, so I'm for the first week I'm going to just reiterate what sir has taught in the week one of the course, and I will be going through the ungraded assignment questions, solutions for the ungraded assignment questions, and then if you have any doubts, you can feel free to ask me that. We have planned some coding part also, but since it's just the first week, so we'll be introducing it in the coming weeks. So yeah, so let me start. So I just want to go through the multi-arm mandate concept that sir has said. So in multi-arm mandates, the underlying assumptions of the the setup is given as you have n arms. You have n arms, and at each time you pull an arm, each arm gives you a reward RT. That reward is stochastic, so that means that each and every arm reward is given from a distribution. We don't know the distribution, so which has an expectation and a variance and all. So you want to maximize the total expected reward that you can get from the arms. So what you want, especially want to do, you want to know the arm which has the maximum expectation for the reward, and you want to pull it multiple times. But since you don't know the underlying probability distribution for all those arms, you also need to like learn the expected reward for each and every arm. So for that you need to explore each and every arm and sample that arm, find the expectation for running expectation, sample running expectation, and then you need to figure out which is the maximum of those arms, and you need to keep pulling the maximum for long time. But the problem is that to get to the accurate value, you need to sample asymptotically. Like the more samples you get, the more accurate you get in reading the expectation of the arm. But then you don't have that much time, so you need to have a trade-off between how much do I explore each and every arm and how much do I exploit the maximum that has. So in the multi-arm mandate setting, so you have asymptotical correctness. Okay, and now the setting that we are doing is that the probability distribution for each and every arm is stationary. So stationary meaning that the probability distribution doesn't change with respect to time. So if at the starting at time t I give you that I don't give you, but if the underlying probability distribution of rewards of arm 1 has a particular probability distribution, that is a probability distribution throughout the whole time. So the probability distribution itself is not changing with time. So that is the basic first setup that sir has done in class. So I'll be explaining the same thing. The probability distributions are stationary. So first thing that you want to look in multi-arm mandate is the asymptotical correctness. So okay, so what does asymptotical correctness say? That you have Q star, you have Q of A. So Q of A, you have Q of A. Q of A is the true expected reward of R1. The true expected reward of arm A in one of the arms. You don't know the true expected reward of arm A. You need to sample the rewards from each arm, and then you need to find the rewards, and then you need to do the sample average, and then you need to estimate this quantity so that you can make a guess as which arm has the highest expected reward, and so that you can pull that expected reward multiple times. So yeah, so this is what you want to do. So now asymptotical correctness means I want to, and let Q star A star be the true expected reward of the optimal arm. So what do I mean by optimal arm? So there will be one arm which has the maximum expected reward. So that maximum expected reward will be given by the Q star A star. So asymptotical correctness is I want to find the optimal arm that gives the most expected, the highest expected reward. I want to find that. So asymptotical correctness is that as I sample to infinity, do I get to know the arm that has the most expected reward, that is greater. Okay. So the second one is regret optimality. So regret optimality is basically you knowing the distributions of all those arms beforehand. If you know the distribution of all those arms beforehand, what you would do is you would always pull the arm which has the maximum expected reward, and you get the expected reward would always be maximum. The expected reward, not the reward at each time instant. The expected reward would be the maximum. Next, you design an algorithm. You have a solution which says that okay, if I pull this arm, then maybe I get the maximum expected reward. Now you plot the expected rewards of your solution, of your algorithm, what you have done, and you check between those two that how much am I far away from the expected reward, optimal expected reward. So what happens is, if your algorithm is asymptotically correct, then as it goes to t is equal to infinity, you will reach the maximum expected reward that gives, if you know the underlying distribution. So if you know the underlying distribution, the expected reward is constant, because you'll always pull the arm which has the maximum expected reward. If you don't know, you want to get something like this so that you reach the maximum expected reward. But since you don't know, since you are learning, there will be some places where you do not pull the maximum expected reward arm, you'll pull some other arm which is not the maximum expected reward. So the difference between these two is what gives you the regret. So there are many trade-offs while studying the regret. So you could not explore too much and just exploit very less, exploit too much, not exploit too much. So all those trade-offs are there. I think some of them are covered in the questions, ungraded questions that have been there. So I'll cover that when I'll go into that. So the third one is pack optimal or pack complexity. So pack complexity is given by two parameters, epsilon and delta. So basically probability of Q star A. So Q star A is the expected reward of the arm which your algorithm gives as the maximum expected reward is greater than or equal to Q star A star. Q star A star is the expected reward of the optimal arm, the true optimal arm. Epsilon is greater than or equal to 1 minus delta. So now, so this is the pack complexity condition that is being to satisfy. Now I believe someone had a doubt in the forum that Sir had wrote probability of epsilon A greater than or equal to 1 minus epsilon Q star A star greater than or equal to 1 minus delta, and Sir has that this is the relative part and this is the absolute part. But the pack setting, basically the pack setting uses this is the correct probability formulation for pack for finding out pack complexity. So when Sir meant that this is the relative and this is a absolute thing, so I just want to give an example that, so Okay, for the relative part, so let epsilon be 0.1. Then 1 minus epsilon will be 0.9. So just as an example, a small example. Now this thing I can write as probability of q star a by q star a star equal to 1 minus epsilon. Equal to 1 minus epsilon. So now if my q star a is suppose 1 0 is 100 and I get a q star a star which is 150, then my this side value would be 100 by 150, which comes out to 0.67 around. So it's not satisfying. But q star is 10,000, very high, and q star a star the same difference, 50, 10,000 50, then 1000 and 10,050 you would get something which is 0.995 or something like that, which satisfies the absolute bound. So the relative bound. So the relative bound is something where you calculate in percentages. So it is not the absolute difference between the what you have. So what your true value is and what your estimated value is. So, but the pack optimality, this is what you will be using for calculating the pack optimality complexity. This is the main thing. So for this, what happens is if you have your expected arm as 150 and you estimate it as 100, then your epsilon is 50. So you're in the range of 50. So that is what this is. That is what sir meant when it's absolute and relative. It doesn't matter how big your true optimal expected value for the true optimal arm was. It is just how close you are to the true optimal arm, not in percentages but absolutely. So I hope this is clear.
Excuse me, sir.
Yeah.
So when this Q star A is very high, Q star A star is very high. In that case, if you use the absolute thing, that is a more stronger constraint, right?
Yeah, actually, yes, you are right. Like pack complexity is the absolute one. It's not the relative. The relative is just that sir has written that, and it is just that it compares the relation how close you are as a percentage issue more than a absolute issue. You're right. Absolute is more stronger than relative.
Okay.
But this is the the absolute one that sir has told in the class. That is what is used for finding out pack complexity. Keep that in. Okay, so next I think sir has got value-based methods.
Sorry, one interruption. What is the delta in that previous example? Yes, please.
So delta is a number between 0 and 1. So it's a probability that you need. So I give you an algorithm and you say like how if I give an algorithm and an epsilon, like you say how much delta, with what probability I can satisfy this condition. So what is the probability that I go epsilon close to my what is the probability that I go epsilon close to my true value, and you write the probability. The delta gives you the probability.
Okay.
So delta is a parameter which is between 0 and 1.
Okay.
So epsilon gives you how close you are. Delta gives you with what probability you will achieve that closeness. So epsilon gives you the approximate, how much approximate you are to the original one, and the probably approximate, the delta gives you the probability part. How probable you are to be this much approximate to the original solution. So I hope that is clear.
Hello. Yeah, delta has to be as small as possible for any algorithm.
Yeah, like it's a design issue. Ideally, it has to be as small. Even epsilon has to be as small as possible, like closer to 0. The more epsilon is close to 0, the more good.
So why not just keep what delta, like 1 minus epsilon, 1 minus delta y is there.
I didn't get you.
Like we put 1 minus delta, right?
Yeah.
So instead of just putting delta, why is so?
So that is the way that it is defined. It's not that you need to define it conventionally. It's defined as that way. It's okay if you put like if you have a delta prime and you say that 1 minus delta is delta prime, and delta prime goes from 0 to 1. That's also fine.
Then,
That delta prime should be closer to 1. That's okay.
so if my probability of getting this greater than some delta dash.
Yeah,
Okay.
that's what I'm saying.
Yeah.
Yeah, that's also fine. That's also, you can define it that way. Yes.
Okay, so then delta doesn't directly give you the probability of this thing being greater. 1 minus delta that gives.
Yeah, 1 minus delta, but delta is the parameter which you use to define the probability.
Okay.
So you have a function of delta, so it's the same thing. Right? So you need a parameter to define the probability. That parameter is delta, which gives you the probability. Like delta is not the probability, but delta gives you the probability in which you approach the function. It's a parameter which gives you.
Okay. Thank you.
Okay, so next is the value-based method. So now I'm trying to estimate the reward that estimate my expected reward of arm A at time B. So that is given by 1, 2, 3. I see how many times I've sampled. So the indicator function is how many times has this event occurred. So how many times has this event happened. So what this basically states is that indicator of AI is equal to Y is equal to 1 if AI is equal to A is equal to 0 if else. I hope this side is visible. Let me write it a bit closer. So the indicator function AI is equal to A is equal to 1 if AI is equal to A, 0 if otherwise. So at the ith instant, if your action, the arm that you have pulled is eighth arm, the arm A, then the indicator function will give you 1. If it is some other arm other than A, then it will give you a 0. So basically what it is doing is it is counting the number of times that you have. So okay, so this summation is counting the number of times you have pulled the arm A in the interval 1 to 2. I hope that is clear. And then you are trying to, the reward at each time instant I divided by summation equal to so this gives you number of times you have pulled the arm in the interval 1 to 3, and this gives you total reward when you have pulled arm A in the interval 1 to 3. So this is your sample average till time t of rewards for the arm A. So okay, I hope sir has taught greedy. Yeah, sir has taught greedy algorithm. So the greedy algorithm is you always, so what arm to pull at time t? What arm to pull at time t? You pull the arc max of Q.
Aniket, can you please repeat the value-based method? The equation doesn't seem a bit confusing.
Okay.
Especially the fraction, the indicator functions. It seems like it can cancel and make it become 1.
No. So this whole thing is in the summation. So this also has a I. So okay, yeah, so let me write it more clearly. Okay, so in the summation we have I is equal to 1 to 2, indicator of A is equal to A into Ri by summation I equal to 1 to 2, indicator of A is equal to A. What you're saying is it can cancel if I could take this Ri common out.
Okay, got it.
The Ri is multiplied with each and every summation term that I'm getting. So at the first time instant you're checking, did I pull A1? Did I pull A? If not, it's 0. Ignore it. Second instant, did I pull A? Yes, I pulled A. What is the reward that I have? So 1 into, what is the reward did I get?
Got it. Yes.
So there is no
Thank you.
point of cancellation. I hope I'm clear. Hello?
Yes, Aniket. Yeah, thank you.
And do you also see that this in a sense gives you the sample average of the rewards at time t?
Yes, that's true.
Yeah. So this essentially what gives you is R1 plus R2 plus 1 RT. But yeah, so I might be writing the wrong thing here because I need to write at what instant also be. So I'm not going to write this, but yeah, I hope this makes sense.
This is for every arm, right? Every arm you will get a sample average.
Yeah, every arm I'll get a sample. You're right. So okay, let me do one thing. Yeah, you're right. Every arm will get a sample. Now if I change the arm to A2, then I have to check at what instance I have picked A. The indicator function would give you at what instance you have picked the arm A2. I hope that is clear. So what you get is you get a sample average for each and every arm at till time t. Algorithm is you always pick the maximum arm. You always pick the action, the arm which gives you the maximum expected reward that you have calculated. You don't know, so the one you have sample average that. So this thing has a lot of problems. So how do you start? So first you have no sample average for everything. So you have 0, 0, 0 for everything. Then who do you pick? Then suppose you uniformly randomly pick something. You pick one uniformly random arm, and then you you get a reward which is positive. Once you get a reward positive, the next time again you're endlessly in a loop which you're picking the same arm again and again and again. You're not even searching whether if other arm gives me a more higher expected reward value. So this is not at all a very good algorithm, and there is no exploration, so there is no guarantee that you will asymptotically be correct. The asymptotical correctness also is not well defined in this type of setting. I hope that comes out from this thing. Okay, so next, I will do the epsilon gradient. So what does epsilon greedy say? Epsilon greedy gives you that with probability 1 minus epsilon, you pick the maximum of the calculated samples because you don't have the true values of your calculated samples, and otherwise you uniformly sample from the whole action space, one to any arm you can use, right? Okay, so just wanted to ask you. Okay, so that's fine. So here we have, so the probability of main section this. So this is your algorithm for epsilon greedy. So here what you get is for probability of 1 minus epsilon, your okay, so it's not 1 minus epsilon exactly. So with probability 1 minus epsilon, plus epsilon by n, I think. With this probability, you are exploiting. So what does exploiting mean? Exploiting means that you are picking the arm which has the maximum expected reward till the time you have calculated all the samples till time. And then you are, with some probability, you are exploring the algorithm. So yeah, so this is one of the algorithm which gives you a trade-off between exploiting and exploring. So yeah, so I think we have some questions on how in the ungraded assignment on how epsilon should be designed. So these all are a design issue of the algorithm, like how epsilon should be, what epsilon values you can use so that you get a good learning rate. I think Sir has also mentioned some of them in the videos that Sir has taught. So if the choosing of epsilon and all is a design issue. So you can start with a very high epsilon and then you can slowly decrease the epsilon. You have to start with a high very exploration rate, and then as you are exploring too much, you start decreasing the exploration rate and start increasing the exploitation rate. You can do many things. So yeah, so that is one of the algorithms. We have some questions regarding that in the ungraded assignment, so we'll go through it, then you'll understand like how changing my epsilon varies the algorithm. So next was, I believe, the softmax. Yeah, so softmax, I'm just directly going to give you the algo. So the probability of you choosing an arm A is given by the expectation of by beta by summation of is equal to 1 to n. So here these i's are arms. So you're since here you have seen that you're calculating the expected sample average, the sample average for each and every arm till time t, sample average for the rewards of each and every arm at till time t. So you add up all the exponentiated sample average of reward of each and every arm till the time t. So and this gives you a probability measure to pick all the arms, So what this does is you have probability now with which you are picking the maximum arm. So the maximum arm would give you the highest value, and as the expected rewards of the arms, sample expected rewards of the arms are decreasing, the probability will decrease for each and every arm, but you will have a similar type of, like, if it is more closer to the higher expected sample average of the reward of the arm, then it will have more probability. If it is very less sample average, then it will have less probability. But yeah, this is also one of the algorithms. So this tells you at time instant t what arm to pick. So these algorithms basically state that which arm you should pick at time t. So if you run the softmax algorithm, it will tell you that okay, at time t the probability of each arm picking is this. Now you have your distribution. Now you just sample up. Once you sample, you can say that which arm you're trying to pick at that instant. So this is softmax, and yeah. So next, I think Sir did the.
Excuse me, sir.
Yeah.
So in the softmax algorithm, so there'll be n arms, right?
Yeah. Then arms.
So we'll have n different probabilities, right, at a given time t.
Okay. N different probabilities. Yeah.
Okay, so the arm with the maximum probability that we are picking, correct?
No. You're not picking the arm with the maximum probability. No. So what you're doing is you are giving a distribution. Okay. So let us take an example. So suppose I have two arms. Okay. So what I'm giving is, suppose arm 1 has the high reward, like it has some 100 reward, and till now the sample expected you have calculated. Arm 2 has, say, 75. So what you're getting is this probability will give you, so pick this, I think it will be 75% of time and pick this 25% of time. Something like that will come, I think, in this software. I'm not sure, you can check the calculation. Yeah, so you'll get some 70%, 20%. So what you're doing is, so once in the next instant, you flip a coin. And the coin is such that it lands head, so you have a coin. It lands head with probability 75.75 and it lands tail with probability 0.25. So now if it lands head, you pick one. If it lands tail, you pick two.
Okay, so even after calculating these probabilities, still it is random.
Yeah. The randomness is there. You're not picking the maximum, the arm which gives the maximum.
Okay, got it, sir. Thank you.
You're basically designing the algorithm in such a way that you get a probability distribution, get an underlying probability distribution, and that probability, using that probability distribution, you pick the arms. And I hope that here you see that both exploration and exploitation are also going simultaneously.
Yes, sir. Yeah.
But the arm with least low value would have less probability to choose. So as the difference between the arms change, the probability of picking the very bad arms go to 0 and the probability of picking very good arms go to 1. So that's what happens as you use the sample size. Yeah, and I think you also need to design beta very carefully. So beta also is a factor which tells how randomness, how much you want to explore and how much you want to exploit.
Yes, sir.
I think I might have mentioned that in class, but
yes, sir. Got it. Thank you.
Ankit, one question.
yeah.
So in this example, the softmax example,
Yeah.
so what are we trying to achieve by, say, even in this example, you got one arm got 100 as the QT and the second arm got 75. So if you substitute this in this formula, you are going to get a value, right?
Yeah. I'm
So-
going to get a value between 0 and 1.
So what does that value denote? What will I do with that value?
That value denotes the probability with which you pick up that arm. So it's not 75%. I don't get the value 75%. I get something which is between 0 and 1. Could you see that this value I'll get something which is between 0 and 1?
Yeah, correct.
I have to
Because, yeah.
It's something of sort of a norm in the denominator. I don't know. So this is 0.75 and this is 0.25. So suppose I get 0.75 and get 0.9. Okay. So what the algorithm tells you is pick the arm with probability 0.75, pick arm 2 with probability 2.25. So what it is saying is exploit with probability 0.75, explore with probability 0.25. The same thing in which greedy, where you had a fixed epsilon. This epsilon is not at all fixed. So it's telling you, okay, that gives you exact probabilities at which to exploit and which to exploit. So now suppose I say that I have 3 arms, okay, 1, 2 and suppose I have 3 arms, where one is 100, one is say 75 and one is say minus 10. So obviously you can see that the third arm is a very bad arm. So if you calculate the softmax for this, you will get something like, this is some 0.6, 0.3 and this will be very low, 0.1. Actually very low. I'm not actually calculating the values, but you get something similar to this. So what we're saying is, the bad arm gets very least probability of you picking. Now 175, they might be close to each other, so maybe with high probability you exploit, but also with some probability you try to sample more of the second arm, which is 75. So that maybe I have sampled it, but I have not sampled it enough times. Maybe that 75, you sample it more times, it will give a more expected cost than 100. So it could increase.
Correct. So that means what, if you do 100 times your experiment, 60 times you will choose arm 1, 30 times you will choose arm 2, and 10 times you will choose third arm. Is that how to interpret this one?
Okay, that is a frequentist approach, but I get your point. It's not that. It's like you're sampling from an like whatever you say is correct. It's not wrong. But you don't have the freedom to do the experiment 100 times. You have to do once. So what you do is you randomly pick. Like next time, So it's random picking. It's not like you do it 100 times, 60 times I pick this, then next 30 times I pick this. You just use the random generator to generate a Bernoulli random variable with 0.75 and 0.5, or you do a multi-level sample 0.75 and 0.6, 0.1. Then you sample out and you do like the one with So the software part, I think the coding part, once the coding part comes, it will come in. But your interpretation is not totally wrong, but that's not how you look at it. You look at it like, okay, with probability 0.6 I'm sampling one arm, with probability 0.5 I'm sampling 2, with probability 0.1 I'm sampling 3. So what it tells you is, I have a very high probability of exploiting arm 1. I have moderate probability of exploring arm 2. I have very less probability of going to arm 3 because I know it is very high.
So in a single shot, you have to add all the 3 outcomes, right?
Yeah. In a single shot, you need. So it could so happen that you do the same algorithm for one sample path, you get different different outcome. I do the same thing, I get a different outcome. It's not the same.
Okay.
But the way you have said it, like expected over the whole time interval, we'll get the same expected result.
And it's mainly because the second iteration, those probabilities will change, right? Because it gets updated with the queues.
Yeah.
Okay. And Aniket, can you? I know you said you spoke about the coding part, but can you tell me which function in Python gives probability based on our predefined distribution?
I didn't get the question.
Like for example, this 0.6, 0.3, 0.1, right? If I want to pick one of these things based on those probabilities, what Python function should I use?
Okay, that is a good question. I can't remember the.
Right. Okay, I'll try to find out. Thank you.
But you can do a sampling thing. So what you do is, you have uniform. You know how to generate uniform generator
Yes.
in probability in this thing. So what you do is, if the number you get is between 0 and 0.1, pick arm 3.
Right. Then you. Okay. Got it. I see what you're saying.
0.1 and 0.4, I think. Yeah, pick second. If it's between 0.4 and 0.1, then pick 1.
Got it. That's another thing that professor explained, right? How do you generate a random number? You have to do cumulative. Yeah. Got it. Thank you.
That thing you can do. Yeah. What else is there? I don't know if there's a function which directly so that you can put the probability values, and maybe there is. I'm not sure.
Yeah, I'll try to find it. Thank you.
If you find it, please put it in the forum also, because that might be useful to me also. Right?
Sure. Yeah.
Yeah, it's not coming on the back of my head, I'm sorry. But I don't remember. Okay, so next. What next is that? Next we have. Okay, next sir told. I think I'm running short on time, but I think it's fine. So next sir did the estimation for QT. Like, you no need to remember all the reward samples, all the times that you have been rewarded. You can just remember the number of times that arm has picked, the arm has been picked, and the previous expected reward, and you can write. Okay, so this is the recursive equation. So what it is, like, since you are doing sample average for lot of time, while doing coding, what happens is, you'll always, sometime you'll run into a memory problem. You don't need to store each and every reward that you have drawn at each and every time, and you don't need to remember at what instant my arm was picked and calculated this whole formula. This whole formula. This whole formula you don't need to calculate every time. You don't need to remember all the rewards. You don't need to remember at what instant of my time my arm was picked. You don't need to remember all of these things, because you might run into a memory problem. while doing coding part. So what you can do is just remember each arm, number of times it has been picked, and the previous expected reward, the expected reward that you have calculated using the samples previously. So that is qt minus 1, and n is the number of times it has been picked previously before this. So now suppose the arm has been picked at let 80 is equal to 8. So the arm that you are trying to update the sample average has been picked at time t. Then what happens is indicator of 80 is equal to 8 is 1. So qt minus 1 na plus rt by na plus 1. So qt minus 1 is equal to the total rewards till t minus 1 into number of times it has been picked up, right? Number of times it has been picked up till previous. I think this formula is clear to you. So qt minus 1 into na will give you the sum of the rewards till t minus 1 when you have picked arm plus, so this is the sum of the rewards of till t minus 1 when you have picked arm plus, since you have picked arm at time t, that reward by this is the number of times you have picked 8 till t minus 1 plus 1. So this is a like iterative way of calculating qt. Instead of remembering the whole sequence of RTs for each and every arm, you can just remember the expected reward of R8 till t minus 1 and the number of times it has been. And sir has also gone further and given a nice form to it, where so that I think you can go through the lecture notes. If you have any doubt in that, you can ask me, but I think that's just a algebraic manipulation of this thing. So okay, so now let me do the ungraded solutions for the week 1 assignment. So yeah, if anyone okay, so I'll read the first question. If anyone has any like idea how to do this thing, you can just unmute yourself and just speak. So the first one, which of the following best suits the notion of regret in a standard multi-arm bandit problem, assuming the bandits are stationary, because we have done stationary. Okay, so the difference between the total, okay, so would anyone like to answer the question? I hope you have tried the Okay. So I'll read each and every option and I'll say what's the plan of this. So the first option is there's the difference between total reward that could have been achieved by choosing the optimal action from the beginning. Total reward achieved by choosing the worst action from the beginning. So that is not a notion of regret. So what regret is you give an algorithm and you find what that, like you give a solution, like okay, pick the arms at time instant 1, at time instant 2, at time instant 3, these arms you pick, and you calculate the expected reward, and if you have known the expected reward, what is the difference between them, not the worst action from the beginning. So the first one is wrong. The number of times to prepare the solution method to find the optimal action, that is also wrong. The difference between total reward that could have been achieved by choosing the optimal action from the beginning, the total reward accumulated by your solution. Yeah, so by our solution method, that is by your algorithm. So you give an algorithm, you can find out what regret that algorithm is. You change the algorithm, you get different results. Even with the same algorithm, you do it different sample paths will have different results. But since you are expected sample path, so you take the expectation, you run the algo multiple times, check the expectation, and then calculate the regret. So that's fine. So give an algo, regret for that algo. Like give your solution, how much worse it is performing from the optimal. So for the first one is third one. Let's read the fourth one. The difference between the best possible outcome sample selecting optimal action and the worst possible result between sample selecting optimal action. No, both times you're not doing the optimal action because you don't know the optimal action. You're trying to find the optimal action. So regret is something, your solution and the optimal, and you want to minimize the regret. I Hope that is clear. Next is the correct assignment problem is the issue of assigning a correct mapping of rewards equivalent to the actions that led to them. Here following the reason for correct assignment problem in RL. Okay, so correct assignment problem in RL is, okay, this is not related to multi-arm bandits, but this is for RL setting. What happens is, if you're not in the immediate RL setting, I think sir has told that in the class, then the rewards are actually delayed. So suppose like in a chess match, you take out the queen of the opponent. That is a very good move, but then you lose the match. So now, was taking the queen away of the opponent but not a good move? Like, how do you assign the winning probabilities? Like, a good action, but the reward was that you failed at the task. So should I decrease the value of the action of taking a queen away? So that mapping is what is a credit assignment problem. Like, which move was the exact move that made you to lose the game. You might play a very good move, but eventually, because of there are multiple steps in the game and multiple moves in the game, you might lose the game ultimately. So losing which move to update the this thing is a credit assignment problem, and that happens in RL because the rewards are delayed in RL set. So that is the answer. Okay, next, consider the following statement for epsilon greedy approach for a stationary event. So you have also seen this. Always keeping epsilon as constant is a good approach. So yeah, so always keeping epsilon as constant is not at all
False.
Yeah, it's a false. Good, thanks. Could you also state why?
Yeah. Suppose epsilon is always constant.
Yeah.
Then what happens is the probability that I pick the maximum argument rate at a particular instant, that will also remain constant, and that will be a very high probability, and the exploration part will be missing.
No, you will continue to explore even when you have achieved exploitation.
So you will not stop the exploration.
Yeah, you will not stop the exploration. The main thing is you will not stop the exploration. You will continue to explore with the same probability, even when you have reached asymptotic stability. You don't want to explore.
No, but I was saying a case where epsilon was very low, so that case was. If epsilon was low and constant, that is a different case, and epsilon was high and constant, that is a different case, right?
Okay. Okay, I think technically it sounds right, but yeah, you're right. That's false. So yeah, so epsilon constant is bad. It's bad in both cases.
Yeah.
So large values of epsilon will lead to unnecessary exploration in the long run. I think that is what your solution, what you just said now. Right?
Yeah, exactly.
Yeah. So the more epsilon you have, the more you'll explore. That is what you
Yeah. Yeah.
Like, that is the opposite of what you're trying to say. Okay, yeah, sure. No issue. So
Yeah, actually, I was saying about the third choice, I guess. Yeah.
okay, cooling down epsilon too fast problematic as current correctness in the value estimates. So I think that is also clear to everyone that the more fast you cool down epsilon, the more you are not exploring good arms. So cooling down epsilon too fast is also a problem. Making it too large for a long run is also a problem. So you need to find the optimal time for which I need to pick an epsilon. So what is it? So here what you have is the second and third are correct. So it's 2 and 3. The first is epsilon keeping constant is not at all a good approach. So the fourth one, I believe it's a mathematical, like numerical solution. So I'm not doing it. Is it okay with everyone? If anyone has a doubt, you can ask. I'll happily go over to it, but I think the answer is 0.2.
I just calculated actually. I saw this 6.23. Yeah.
Yeah, it's 0.2. Okay. No issue. Okay. So this is the last question. So coming to the function, the rewards are obtained at a fixed time. Okay. The rewards are obtained at fixed time after taking an action. No, right?
No.
Because different settings would give you different times at which you can get the reward. You can
Yeah,
have
only immediate RL problems will.
Okay, yeah. So I hope that is clear to everyone. Reinforcement learning is neither supervised nor unsupervised. I think that is a point that Sir has stressed in his videos a lot. Like it's not supervised, it's not unsupervised learning. So 2 is correct. 2 reinforcement learning agents can learn by playing against each other. So that is true in a sense. So there have been cases in AlphaGo where chess or Go where 2 RL agents were pitted against each other to learn. So what they did was they made both of them play randomly first. Both of them randomly. They learned something, and then after that they stopped updating one of the RL agents. They made one RL agent update itself and become better than the opponent. Now once it became better than the opponent, then they stopped updating these guys' algorithms and they started updating this guy. So it became better than this. So each and every time they would benchmark, they would be better. So that is also where how 2 reinforcement learning agents can play against each other and learn. There are multiple ways, and also this is the only way. There are multiple ways with which 2 reinforcement learning agents can play with each other and learn. So Lord also.
Actually, I had doubt in this particular option, but the solution that you're saying seems interesting because I didn't think of this. That they're alternatively.
Yeah, they're alternate. So first you make them play randomly, they learn something. They learn
Okay.
something randomly. And then you don't update one, you update the other. It learns something which is better than the X1. And then you stop updating this. Since this has a benchmark, this learns something and it becomes better than the other one. This was done due to complexities or something, I'm not sure. But
Okay. Okay, sir. Yeah.
always selecting the action with maximum reward will automatically maximize the winning probability in a game. Okay. Does anyone have a comment on this?
There's no chance of exploration, right? If you always choose maximum reward.
Yes. There's no chance of exploration, and in the RL setting, it could so happen that you play a very good move, a move with maximum reward. But once you play a good move, the next state that like you have a chessboard, you play a very excellent move. That is like one of the best moves that you could have played. But once you play the move, you have landed in a state where winning for you is very bad. So it depends on what state you are, right? So what the chessboard is. It might be a good move, but some other time. But given this state, it is a very bad. So those things comes into it. Because you don't have a reward which comes immediately. You have a sequence of, in a game, you have sequence of then and then you get a reward. Am I making sense?
Yeah.
So the answer is 2,3. So I don't know whether this meeting would suddenly abruptly stop at 7. But yeah, I just wanted to ask one question to you guys. Okay, so what happens if the underlying expectation of 2 of the arms are same? What do you do?
We do not know, right? A priori.
You do not know a priori, but what if they have the same expectation? What do you think?
Then their Q values may most probably be close or the same.
Yeah, be close or same. So now my question is, maybe they have a probability distribution. One has very high variance and one has a very low variance with both the same expectation. Which one would you like to choose?
The one with low variance.
But does your formulation here take into consideration the expectation of the variance of the?
No, we do not look at the variance.
No, we do not look at it. So that is a problem, I think, which now many of them are looking into some risk-based multi-arm bandits. That's just for your, like if you're interested, you could go and look into it, but that is nowhere related to the course for the RL. This is the main thing. So yeah, so this thing is just for your food for thought, like for today. You could go and check out risk-based multi-arm bandits or something, I'm not sure. But this is also a good interesting problem where new research is coming. So yeah, so I know I've left very small time for your doubts. Do you have any doubts, or should I?
I have one general question though.
Yeah, yeah, sure.
So far, what we understand is this application of RL in real world. Other than gaming, is there any practical scenario where we can apply this RL?
Oh, yeah, like there are many practical scenarios where it can happen. There are many practical scenarios. Okay, robotics is a I don't know which department are you from? Like what are you?
I work in retail and supply chain.
Okay, so RL I think initially was formulated for inventory control. Have you have inventory control is something where okay, so you have 2-3 types of materials that you want to sell. You don't know the number of people that will buy the materials. That is random and each and every amount of it. So how much amount of inventory do you need to buy at the next day? That is your action. Suppose I have product A, product B. I have a warehouse where I store product A and product B. Now, next day, how many people choose product A, product B? It's totally random. Now, your action is to order for the next day. Do I need to order more product A, product B, so that I don't over exceed the limit that I can store in the warehouse?
Okay.
So that makes that in that sense you're learning what action to do at each and every. Does that make sense to you in the real world setting of application? And something is related to retail.
Yeah. Yeah, but as you said in one of the questions, it is not supervised learning though, but how it cuts by itself. That's what.
Those things I think sir will go through. Like
Okay.
we'll have state space. I think we also have a inventory control problem for coding. I'm not sure inventory control is there, but yeah, since you mentioned retail, I'll try to look up inventory control for R.
Okay.
You can also search on Google inventory control for R. There is a how, but that is more as it goes forward you'll get to see, because now sir has got modeled NPTEL and states and all. It's just pure multi-arm managed setup. So once you go more deeper into it, you'll just get it.
Okay.
So I have a question. Just as a thought experiment, if we let two RL agents play against each other for infinite amount of time, then will any one of those agents will play better than it could have been played if they could have been playing with a human?
Oh, that's a good question. Yeah, like I don't know the exact answer to that question, but what I think what will happen is, uh, if it is playing versus a human, the human would have a expert cap, like it a human, you might be different expert in that game, I might have a different expertise. So if an RL is playing against you, suppose you are more better at the game than me, and if an RL agent is playing with you, it will learn more than what it will learn with playing with me. Does that make sense?
Somewhat.
So the more expert the RL plays against, the more it will learn.
So you are saying that RL needs diversity while training, is it?
I see that is why I don't want to make a statement, because it all depends on what algorithm the RL is learning on and what algorithm you are using. Those also play a part. Right? So I don't want to make like full close statements that yeah, this is done. Like if you do this, you'll get good result. So it depends on what algo you are using. But I think these questions, what you're asking, they'll naturally come up to you once you see what all algorithms are being using in the RL.
Okay, sir.
This is the theoretical part of this. You'll get to understand which is better.
Hey Aniket, hi Rakesh here. I have a general question. So I'm right now working on a control. So can you tell me how the RL will be useful to work with the controls algorithm?
Oh, controls.
Let's say I'm working on optimal control to be more specific.
Okay, okay, yeah, optimal control is RL. Like you're trying to find like okay, so you know optimal control, right? So optimal control, what it does is you have a model x dot is equal to x plus b. You try to minimize some cost. So you're trying to find a trajectory x. You
Yeah.
find a trajectory u such that you minimize this cost.
Yeah. So
Yes.
basically, we have a cost. We minimize that
Yeah,
thing.
yeah, yeah,
Minimize
yeah,
the cost, and
yeah.
for that we got optimal policy, which we
Optimal
use to
policy.
update the next
Yes,
state.
yes,
Yeah,
yes.
that's the pretty much.
The,
So
so
my question is here. Yeah.
RL is basically optimal control where you don't know what the model is. If that makes sense.
So it can also learn the model, right? If it given the sets
So
of data,
yeah,
it
so
can learn the model.
yes, so than learning a model, it's better to like just interact with the environment and see when it is doing good, when it is doing bad, and get the optimal
So in
policies.
this course, are there any related to controls algorithm? I mean, not the control a specific means the learning based model and all that in this course.
Uh, okay, I think okay. So the one of the main part is the policy that you see here. So it's basically optimal control. The nomenclatures are different. So in optimal control, you have control trajectories, right? So the policy that you see here, that you will see here. Sir has not yet stated what a policy is like. He has not defined properly. But once he will define it, so once you will see a policy is basically your control trajectory. Like
I think yeah, policy is basically the control trajectory, and the reward is basically that cost.
cost function, yeah.
Yeah.
And once sir introduce MDP and all, you will see how state trajectories also vary. So you have state trajectories which vary, how the state trajectories vary, what are the probabilities, how to model how to not know the model and still try to learn the model. All those things I will go into.
Okay. Thanks. Thank you very much.
Thank you, sir.
Uh, so
Thanks and give. Thanks.
yeah.
Thank you, sir.
So
Thanks,
feel free
Ankit.
to
Thank
keep.
you, sir.
And if you have any doubts, I'm staying back for 5 more minutes. So
Thank you, sir.
Thanks, Aniket. It was an awesome session. Thank you.
uh,
Ankit, if you allow me, let me go back to the softmax dumb question which I
oh yeah,
had.
sure. Okay, just a minute.
Yeah.
Yeah. Okay.
So in the softmax example, whatever you showed, the point six point, yeah, that one. So that is going to be a list object, right? When you compute, you are going to, because you have three arms and the probability of AT is equal to A, you are going to get 0.6, 0.3 and 0.1.
Yes.
So now, so assume you have done some 1,000 experiments and you arrived at this value.
No.
Now,
No. I didn't get you.
uh,
So,
so
I have not. I have not done 1,000 experiments and arrived at this value. I'm giving you the algorithm for which you need to pick up. Like at time t, with this probability you need to pick this up. Like okay, so okay, how do I say? So if I do okay till time t minus 1, everything I have done is same. Okay, I have not changed. Till t minus 1, whatever I have done, whatever rewards I got is the same as 175 minus 10. Now, now at time t, that time t instant I am doing it 1,000 times. Then I should get 600, 300 and 100 or something. Let me calculate. No, 600, 300 and 100. Then I should get 600, 300 and 100 as we have said. It's not that I do the whole experiment for whole time. Because if I do it the whole experiment again, at time t I might not get 100 for 1, 75 for 2, minus 10 for 2. I might get something else. Because they're random.
okay.
Do you understand the problem?
So what does that mean? From the very first time t is equal to 1, you have to split between exploration and exploitation, is it? But at least you need some history to have some idea of basic stuff.
So first instance, first algorithms, what you do is suppose you take everything has zero reward. Okay.
Right.
then you get everything probability would be 1 by n, 1 by n, 1 by n, 1 by n, 1. So it's uniformly random.
Correct.
First step.
It's
You pick
same, yeah.
something. Yeah. So you pick something. So uniformly random matlab anything is fine. Pick something random, uniform, because everything has same probability of picking.
Okay.
So you pick something, you get a reward. Then the probabilities for picking each of them changes.
Right.
Because the probability of picking of arm A is dependent on what the expected value of arm 1, 2, 3, 4 to n is.
Okay.
So probability of picking all the arms change. It's not just one arm which you have picked.
Correct.
So now you have a probability distribution. P1, P2, P3, discrete probability distribution.
Right.
So now given a discrete probability distribution, okay, so now what I'm saying is, okay, so suppose I have x as a random variable, okay, so I have x can take values, x can take values, x is a random variable which can take values between 0 and 1. So probability of x equal to 0 is say 0.7, and probability of x equal to 1 is say 0.3. Okay?
Okay.
So now I tell you sample x, like give me one sample of x. It could be 0, it could be 1, it could be anything. But
Okay.
more number of times you pick, you'll see that more number of times you get 0 than 1.
Okay.
But when I tell you to sample once, you will always sample, it might be 0, 1, it is random. So the next time instant, I'm telling you to sample this x. Just one time. Depending, I'm giving you this probability, I'm telling you to sample this randomly. This is the random variable.
Okay.
So I'm telling you, randomly sample one arm using this probability. You might get the worst arm, but the probability of getting the worst arm is very low in the next instant.
Okay.
Am I making sense? Like, is it?
Yeah.
And how do you do that computationally? Is something someone has asked that if I have something between 0 and 1, then I uniformly generate a random variable, say 0 to 0.1. And if the number is between 0 and 0.1, I pick arm 2. If the number is between 0 and 0.4, I pick arm 2. If the number is between 1.1 and 1, so if it is between this, I pick 2. If it is between this, I pick 3. If this is between 0.4 and 1, I pick 1.
Okay.
So as you can see, the probability measure here is 0.1. Here it's 0.3. Here it's 0.6. So
Okay.
what is the probability of your sample point falling in this region? It is more, right? Than this small region, which is 0.1.
Okay.
So next time you can pick the worst arm, which is 3. That is no problem. But as you go on, most probably you will be picking the arm with the maximum result, because probabilities are so assigned.
Okay. So are these values also going to change every time, or
Yeah.
is it going to remain constant?
No,
Okay.
no. It's going to change. You are going to update it every time. These values are going to
Okay.
update, and then if you design betas in such a way that like you need to change beta, like that is the learning rate, that is the epsilon, that is something which is the epsilon of you need to modify epsilon. So if you need to modify beta here. So the softmax are given here is you need to modify the beta. So how to modify the beta? There is a design problem. When to change beta, when to decrease beta, when to increase beta, those things. But yeah, it is going to change every time, and as you get as this gets farther from these things, the probability of picking this thing keeps on increasing.
Okay. Got you.
Excuse me, sir. Can you put some interesting blogs in our forum so that we can read in further?
Okay, sure. Yeah, I will try to do that.
Okay, sir.
Just put a reminder on the forum for some interesting books. I will.
Okay, sir.
Okay. So I think I'll end the meeting.
Thank you.